the next session of this rubber industry tips and tricks. This is very useful for the people in the industry who want to improve their process. And we have invited various experts to talk about these tips and tricks. With a huge experience, they are sharing some of their the tricks and tips and tricks in this session. Today, we are covering on the topic on the rubber compound and process design to reduce backrinding. And this session is taken care by Mr. Pranab K. Bhattacharya. Let me brief about Mr. Bhattacharya. He is a well-experienced rubber technologist with close to 28 years experience. Currently, he is working as a technical manager at JMF Synthetics, India. He got a rich expertise in the adhesion science and technology for plastics and rubber to metal bond composites. And his major expertise involved material selection and a new product development by designing compound in general purpose as well as the specialty purpose rubbers. He has worked with a number of companies like J3 Polymers, Ramaco Overseas, ACE, Volcom, with Elastomer Processor, Suzanne Group, Premier Sales. So, Mr. Pranab is sharing, his experience into the tips and tricks session. Just give you additional information. He also contributed the know-how webinar, one on focusing on the rubber to metal bonding, case studies and troubleshooting. And also, I think like today's tips and tricks, he did in the past sessions, EPDM rubber compounding. If you check our rubber industry news server, you'll find this session on the tips and tricks focusing on the EPDM rubber compounding. Okay, let's look at the the presentation on the rubber compound and process design to reduce backrinding.
Hello everyone, welcome to Tips and Tricks session of News Hour, an initiative by Technobiz. In this session, I will talk about rubber compound and process design to reduce backrinding. Rubbers are vulcanized or cured inside the mold through the method of compression, transfer, and injection molding. Molds contain 2 or more plates, and parting lines are generated on final products. A thin, uniform parting line on molded components is the requirement. However, many a times during processing, the parting lines are found to be non-uniform, wavy, and foamy in nature. During deflation, these parting lines are torn and produces cracks. This defect is known as backrinding. So what is backrinding? Backrinding is a molding defect, appears as a rough edge observed on parting line during molding of elastomeric components. Scorched foamy rubber generates on the mold line during flash removal. This scorched and foamy rubber propagates cracks on the product across the mold parting line. This results a defective product. What is the plausible reason of backrinding? During molding, the mold is kept inside molding press at higher temperature for vulcanizations. In case of compression molding, preformed blank of mixed rubber is kept inside the mold cavity directly, and pressure is applied at high temperature through molding press. In case of transfer molding, the rubber is kept inside a transfer pot and pressure is applied through a plunger so that rubber can flow inside the cavity through transfer holes. In both cases, rubber transforms from semi-solid to liquid or semi-solid state inside the core cavity. This liquid or semi-liquid inside the core cavity is incompressible in nature. The mold is heated, and under heat, the liquid of the core expands, that is, thermal expansion takes place. Due to this thermal expansion, the liquid flows and applies tremendous pressures on the mold. The pressures sometimes sufficient enough to open up the mold on its putting line to allow the molten rubber to flow inside the cavity. But the heat history of the rubber adjacent to putting line is different. It may so happen that rubber adjacent to putting line is permanently partially cured or scorched. If the ejected polymer is partially scorched, then flaws appears on putting line, and this is known as backrind. So the plausible reason of backrinding is thermal expansion forces partially cured rubber out of the mold, and uneven wavy surface generates on putting line. This is essentially an imbalance in rate of cure between the surface and the core material. However, backrinding may also be caused by bars or roughness of the mold on the putting edges or excessive mold openings. How to characterize the compounds to assess backrinding? Four important compound and process characteristics can be considered to assess the backrinding of compounds. The first one is the minimum torque or ml values of the compound. This we can get it from rheometer. Second one is the scorch time, TS5 of the compound. Again, this we can get it from rheometer. Time taken to travel the rubber from the bottom to putting lines. This is very difficult to assess in conventional rubber industries. The fourth one is Muni viscosity of the compound. So out of the four parameters, three parameters is measurable, and these three parameters can be used to assess the backrinding capabilities of the compounds. A very low ml values can generate backrinding. Also, at too high ml values can also be responsible for backrinding, associated with other molding defects related to mold filling. So we need an optimum ml or Muni viscosity of compound. This needs to be studied and standardized by change in mixing parameters of the compound mixing. So mixing sequence and mixing parameters have equally important part on backrinding. The more the scorch time, the better is the safety of the compound, and the lower is the tendency to backrinding. Is there any effect of type of rubber on backrinding? Backrinding may occur in any kind of elastomers, especially if the item is thick. It is compound, process, and product specific. Compound, when processed differently, may reduce the backrinding effect. Also, the same compound and same process might generate backrinding if the component differs in size and geometry. tendency towards backrinding can be assessed with regard to polymer. It can be generalized based on thermal expansion behavior coupled with the cure characteristics. Tendency towards backrinding can follow an order. ACM and FKM compound has the highest tendency towards backrinding. Next comes silicon. Peroxycure NBr and peroxycure EPDM has higher tendency of backrinding compared to sulfur cure EPDM, and sulfur cure general purpose rubber has the lowest tendency to backrinding. Now, we will briefly discuss on factors to control backrinding on different type of compound. First one is controlling backrinding in ACM compound. Polyacrylic rubbers are made from different acrylic monomers with different molecular weight to adjust oil resistant and low temperature properties. Conventionally, general purpose and high heat resistance grades are available. ACM rubber contains different cure sites and different cure systems are used to manufacture molded goods. Commonly used cure sites are epoxy cure sites, chlorine cure sites, carboxyl cure sites, and dual system of carboxyl and chlorine cure sites. Nowadays, epoxy cure systems are used less, and ACM with chlorine cure sites are widely used for general purpose molded ACM components. In chlorine cure sites, triazine cure system and soap sulfur cure systems are mostly used. Triazine cure systems offers faster cure rate, but with reduced scorch safety. Considering the better process safety of soap sulfur cure system, the triazine cure system can be switched to soap sulfur cure system to reduce backrinding if observed on components. Stearic acid is often added inside the compound. This acts not only as an effective process aid, but also as a retarder with most cure system used in ACM rubber. So an overall balance of stearic acid with certain process aid needs to be obtained to reduce the backrinding. Cure chemicals like potassium stearate and sodium stearate contains moisture and difficult to disperse. Some amount of moisture level helps in dispersion. So choice of proper quality of sodium and potassium stearate is required to reduce backrinding. Time and temperature of mixing inside the kneader is required for achieving optimum ml and monoviscosity to reduce backrinding. Mixing of ACM rubber is very important to control monoviscosity and minimum torque values. Master batch is advisable to be mixed in kneader. The time of mixing and dump temperature should be standardized. The master batch needs to be cooled down, and final mixing should be done in cold mill in two-roll mixing mill. Variations of mixing procedure will change the viscosity and thermal expansion behavior, along with the change in cure characteristics, leading to defects like backrinding on the molded product. Another aspect of ACM rubber is that polyacrylic compounds with carbon black reinforcement gives the appearance of scorch upon beam aging, that is during storage. This beam aging can generate higher backrind defect. It is advisable to check the Muni viscosity of compound before use, and if the viscosity rise is more than 10 units, the compound is scorched and cannot be used. It will definitely generate backrinding along with other molding defects. However, if the rise in viscosity is less than 10 units or minimal, then remilling in cold mixing mill can refresh the compound. Next, I will come on controlling backrinding in bisphenol cured FKM compound. The major difference of FKM is the higher thermal expansion than most rubbers. This higher thermal expansion of core cavity or core rubber exerts force on pre-cured rubber on the surface, resulting in backrinding. This is prominent even in preparation of 12.5 mm thick compression set buttons for testing. During preparations of compression button, especially if it is a 3-plate mold containing 2 plain top and bottom plates and core cavity in middle, the flash in one plain plate often shows backrinding defect, but the flash line adjacent to other plate does not contain any backrind. Similarly, in components with 2 parting lines, it is observed that backrinding effect is prominent in one side of the parting line, but the other side of the parting line is smooth and uniform. Typically, for curing, 6 pHr of calcium hydroxide and 3 parts of magnesium oxides are used. Different ratios can be used with 3 pHr of calcium hydroxide and 6 parts of magnesium oxide for better bonding to metal inserts. The entire cure system is used in conjunction with the metal oxides, which acts as acid acceptors in all systems, capturing hydrogen fluoride formed during vulcanization. To avoid backrinding, we need better scorch safety. A few actions can be taken to reduce or eliminate backrinding. Addition of few parts of calcium oxide in compound can help in reducing backrinding. In case of compression or transfer molding, preformed or blanks should be warmed before use. Simple example is preparation of compression set button. If we prepare the cylindrical blank by rolling a thin sheet from one mixing mill, followed by cutting in required weight and fill the cavities in cylindrical preform, in one condition, tendency of backrinding is reduced drastically. Temperature of molding can be reduced for effective slow curing and better scorch safety. Next is controlling backrinding in peroxy cured silicone rubber. Silicon rubber in peroxide system during compression or even in 3 plates or 4 plates transfer molds generates backrinding across the flash line. So we need to select a suitable grade, preferably with low thermal expansion. If compression molding performs, they should be heated and they should be approximately the shape of the mold cavity and should contain enough rubber to fill the cavity and produce a slight flash. As I told, with compression molding in particular, keeping the molding temperature near the low end of the vulcanization temperature will reduce scorch. Avoid using external silica filler to adjust the hardness or cheapening the compound. This will certainly lead to defect like backrinding. Next is controlling backrinding in peroxide mineral filled EPDM rubber. So EPDM rubber can be cured by both peroxide as well as sulfur cure system. In case of peroxide cure sulfur EPDM rubber, it is advisable to use non-oil extended EPDM rubber. Next is avoid using antioxidant, especially paraphenyl diamine antioxidants, phenolic resins, aromatic and naphthenic oils. Unsaturated fatty acids should be used as minimum as possible. In case of clay-filled rubber, some parts of magnesium oxide or calcium oxide can be added to maintain the pH of the medium. We often add silica in open mixing mill for the purpose of increasing elongation or tear resistance to avoid backrinding. But this procedure should be strictly avoided. Silica should be mixed in internal mixer with coupling agent. Concentrations of the sealant coupling agent should be determined based on amount of the silica filler added. Silica sealant mixing temperature must be maintained for effective compounding. It is advisable to heat the silica filler in oven prior mixing to reduce the moisture content, especially in case of peroxide curing of the EPDM rubber. Use of some amount of calcium oxide in silica filled compound is recommended to avoid backrinding. And finally, use of preform design nearly similar to the mold cavity is recommended. Lastly, I will talk on controlling backrinding on sulfur pure natural rubber. First parameter is improve the reversion resistance of the compound. In case of thick articles, there is a tendency to dissimilar state of cure in natural rubber compound. The high heat history near partition line has a tendency to reversing the state of cure compared to the core. This phenomenon leads to parting line failure and commonly known as burning a parting line. Use of reversion resistance cure additives can reduce the phenomenon drastically. Some of chemicals are N-indus metaphenylene bismaleimide, available as Volcano PM, from Auchesinco Chemical Industry Company Limited. Next is use correct weight and blank shape of preformed article. Reduce the cure temperature as low as possible. Apply higher molding pressure. Use delayed action accelerators with optimum doses of PVI to ensure the base process safety of the compound. And finally, ensure proper mastication and order of mixing of chemicals during mixing. Thank you all for joining this session of the tips and tricks. See you next time.